Okay, we are ready. So I said yesterday that the next 3 units are all kind of related. It's looking at classification of matter, and like physical properties and chemical properties, characteristics of different materials, how we group things. So a lot of this is going to be review, all right? There is going to obviously be some new stuff, but some of it is going to be review, which is nice. Kind of we can just build on what you have already learned over the last couple years. So one thing, and I had mentioned this yesterday, the state of Ohio has density in like 3 or 4 of our units. And so it's worked out good the last couple years when I made density its own separate unit. So when we get to it in another chapter or another unit, it's like, oh yeah, we already know density. It's not like we have to stop and do density to make it fit into that unit. So it's worked out pretty well. So you'll see on your note packet, you have like slide 1, 2, 3, 4, 5, 6. So it kind of goes across and then down, across and then down. And you can see that there's slide numbers at the bottom left of each slide, so you can kind of follow along if you're trying to see like which direction you need to go. Thank you, I got your post-assessment yesterday. All right, so density is a physical property, and it's the property that identifies the amount of mass and the amount of space that something is taking up. All right, that's what density is all about, mass and volume, basically. All right, and so physical property is, there we go. When we're talking about characteristics that we can observe without changing the chemical composition of the item. So if we're talking about like its color, its shape, right, those things, its size, you're not changing what it is you're dealing with. If we would change what we're dealing with, that's a chemical change. So we're going to have a whole unit where we talk about physical versus chemical changes, but just understand that density is a physical property. So it's basically describing, something, describing a certain material or substance. So for example, I can take a piece of paper and I can rip it in half. Each piece is still paper, right? I didn't chemically change it. It's not like I burnt it, right? Where it's no longer made of the same molecules, or it's not where it's the same material as I started with, right? So anything that doesn't change what it's physically made of is considered a physical property. It just changed its shape or its size, right? And so the 2 new halves of paper are still paper even though their size is smaller, okay? And so we're going to be looking at a lot of different types of physical properties over the next couple units, and density just happens to be one of those. Okay, so now back to density, and like I said, you have just a few little blanks on each slide that you're filling in. And since density is a physical property, it's over here, guys. They're still there. They're gone. Okay. This means that each substance has its own unique density. So density is a way to identify. So if I say water has a density of 1 gram per milliliter, that is a unique and identifying characteristic of water. There are charts where you can look up the different densities of all the different elements in our world. All right, we're going to actually do a lab where you're going to be given 3 or 4 cylinders that are the same size and shape, and you're going to try to determine what metal they're made of. So you're going to find the masses, you're going to find the volumes, and you're going to calculate the density, and then from the densities, you're going to look at the chart and you're going to be like, oh, okay, this is lead, this is aluminum, this is copper, right? And so if you know the density, you can identify what the unknown metal would be, because it's a unique property for that metal or for that element if you're dealing with something other than like our little metal cylinders that we'll use. So there is a formula. And again, this is the first time that you guys have been given a formula. This is our first equation we're going to use. And so this is it. Density equals mass divided by volume. When you see this little slash, that's representing like a fraction, like division. So mass divided by volume. Okay, where D is density, M is mass, and V is volume. And so we're all very familiar with mass and volume, nothing too tricky there. We will review it just to make sure that we're all good. But units are gonna be very important. Units were kind of an issue with the half-life calculations. As I've been grading the tests, if it said, what's the half-life of cesium, half-life should key you in that you're talking about a time, right? Some of you said grams, like you gave me 30 grams. Well, 30 grams is not a half-life. Maybe 30 minutes would be, or 30 hours, or 30 years, but you have to match the units with the variable that you're talking about, or with the answer you're talking about. And so that's gonna be a huge thing, and it's not unique. Units usually tend to be an issue for everyone, so don't feel like it's just something that's going on with you guys. It's a thing, right? And so we try to put really, really close attention and focus on units, just because I know it usually can be a problem. So units are going to be helpful. They can help you kind of decode some of the numbers, like, okay, well, what is that variable? What is that information that they're giving me? Is that a mass, is that a volume, or is that a density, right? And so when we're dealing with these three variables, D for density, common units are going to be a mass unit divided by a volume unit. And you're like, well, what's mass and volume units? Well, mass units are typically going to be the gram, the milligram, and usually the kilogram. Right, those are going to be our common. I think you're just filling in these letters in front of your equal signs. And then volume is a little bit trickier, because let's face it, you can have volume of a liquid, but you can also have volume of a solid. And so there's two different units that are involved with those. So if you're talking about a liquid, it's going to be some version of the liter. So like the milliliter, the liter, or the kiloliter. Also notice how I have the L capitalized so that it doesn't look like, if you just make it like this, ML like that, sometimes that little stick version of an L looks like a 1, and we don't want to get anybody confused, right? So capitalize the L for liter. If we're dealing with solids, so like this book, or a triangle, or a cylinder, it's a solid, and we're going to use some version of a length unit cubed. And we'll go over that a little bit more on another slide. So you could have a liquid, you could have a solid. The units will tell you what it is you're dealing with. If the problem doesn't come out and say you have 20 milliliters of liquid cough medicine, if it just says you have 20 milliliters of cough medicine, the milliliter, the liter part would tell me that I'm dealing with a liquid. So I'm dealing with like a liquid version of cough medicine, not a, a pill, okay, which would be a solid. So that can be helpful. And so if you're reading a problem and you see grams, well, then automatically you know that that number goes with the mass. If you see a milliliter, then you know that that number is describing a volume. All right, so the units can actually help you decode what the numbers stand for. Because it might not come out and say the mass of this is, or the volume is this. It might just say, it is 50 milliliters, and you're like, oh shoot, is that milliliters, is that gram, or is that a mass, is that a volume, is that a density? So the units are very specific and they match up. So if you know what the units are, it can help you identify which of these variables you're dealing with in the question. And we'll go over a lot of that, obviously, when we get to our practice problems. Okay, so I want to make sure that you guys are comfortable with what mass and volume really mean in our science terms. All right, so for mass, because these are the two variables obviously in our equation, it's the amount of matter or stuff that's in an object. Okay, and we talked about this a lot last year when we talked about mass versus weight in 8th grade. And so mass is the amount of stuff. Obviously gravity doesn't affect mass. Mass is always the same. If you're talking about weight, then, and sometimes we use those words incorrectly in our everyday life, right? If we're talking weight, that's the pull of gravity on an object, all right? So we're talking not about the pull of gravity, but we're talking about how much stuff is making up that object, okay? So how much matter is in that object? And there's 3 states of matter. We're gonna have a whole unit on this: solids, liquids, and gases. We also have a 4th state that we'll talk about, which is the plasma state. Yeah, Dylan's excited. which is like the gases on steroids in a way. Like they're super hot, they're super excited, super heated. And so basically the electrons are kind of free floating in a plasma state versus our normal gas state where they stay with the atom. So we'll talk about that more when we get to that unit. But our three main ones are solids, liquids, and gases, because the plasma state is happening in our stars, right? That's our fusion situation happening. So there is a lot of plasma out there, but mostly here on Earth, we're dealing with these three. All right, so the base unit for mass is always going to be the gram. You can have the bigger version of that, like the kilogram, by putting that kilo prefix, or you can have the smaller version, like with the milligram. But either way, if you see that G, you know you're talking about mass. Okay, so the kilogram, kg, is for bigger amounts, and then the milligram, and we said last year, like the milligram is like the size of a single grain of salt, right, or single grain, like granule of sugar. The kilogram, I think I might still have it. Yeah, this is my 1 kilogram bag of M&Ms, right, and so each M&M is a gram. So 1,000 of those grams makes up my kilogram. So if we're talking something heavier with more mass, we'll use our kilogram. If we're talking something really small, like typically medication, like 200 milligrams of ibuprofen, right? It's in milligrams because it's a very, very small amount. It'd be like 200 granules of sugar would be that same mass, as that ibuprofen medication, okay? So volume, and volume is a little bit trickier. The concept of it is very easy. It's the amount of space that something takes up. You might also hear this called the capacity. Capacity meaning the same thing, right? So if you see outside the gym, it says maximum capacity, and it has a number of how many people should legally fit in that gym and still be in the fire code, like where we're safe, where if there was an emergency, they're saying all those number of people could exit in a safe manner, quick enough, and all that. Same thing like with elevators. You'll see like maximum capacity, and it might say people. Sometimes it'll even say like kilograms. Like, so how much mass can fit in that elevator with the elevator still functioning, the way it needs to function. All right, so it's basically the amount of space that an object is taking up. So our little pipette is going to measure small amounts for a milliliter. And when we do one of our labs, you might use a pipette to transfer small amounts of liquid into the graduated cylinder. Okay. If we're talking a solid, we're going to be talking about a length unit cubed to the third power. We talked about this last year. If you have a cube, you're looking at length, width, and height. You're dealing in 3 dimensions. That's where that cube comes from. You're looking at 3 sides of something. You're taking a centimeter times another centimeter. That is centimeters cubed, or to the third power. Okay? And so one thing that is pretty darn handy is that 1 milliliter of liquid will perfectly fill a 1 by 1 by 1 centimeter cube. So if I had a centimeter cube, 1 by 1 by 1 centimeter, about this size, and I took a milliliter of water and I put it in that cube, that 1 by 1 by 1 centimeter cube, it would fill exactly that cube. So 1 milliliter is exactly equal to 1 cubic centimeter, or 1 centimeter cubed. And so that lets us kind of be able to mix water volumes with, which, is a liquid, mix our liquid volumes with solid volumes. And this becomes important when we deal with water displacement. So yesterday, Bill and I had a huge part of that video on water displacement. All right, so we'll talk about that here in just a second. But a centimeter times a centimeter times a centimeter is making that centimeter to the third power, or cubed. And so that's where that unit comes from. It's not just a centimeter anymore. It's a brand new unit, which is the cubic centimeter.
We can use the water, the water plus a solid. We could use that for the density by just taking away the waters, the.
Oh, how much water gets moved?
Yeah, how much water gets moved. We just take away the water, then we get the actual density of the solid object.
You're exactly right.
Yes.
Yep, and we're gonna actually do that. You're gonna do that in one of our labs. So you're gonna find the volume by using water displacement.
And plasma is found in stars.
It is. Yep, you're exactly right. So the 1 milliliter liquid is exactly equal to the 1 cubic centimeter, or 1 centimeter cubed. So it becomes a very handy equivalency that we can kind of manipulate for whatever we need. So with volume, if we're dealing with a liquid, okay, so if we're talking liquids here, we can use a graduated cylinder. And I have a cheat sheet that I'll give you. We'll do a little bit of a review on that. But last year we spent a lot of time looking at the graduated cylinder, looking at how to read that. So we'll do a whole little mini review on that before we need it for a lab. But here's our graduated cylinders, right? And so if we have an initial volume and we find that, and then we put in our unknown volume, which is a solid rock, I put that in, then I look at the final volume, right? So if I have like 200 here and 300 there, if I subtract those, the difference is caused by the rock that I put in. If I'm trying to find the volume of the rock, that's pretty handy, right? Because the water that got displaced or moved from its original position was moved because this rock is now taking up the space where that water had been. Okay, and we're assuming it's water, it could be any liquid. So that is the displacement process, and so that's what Bill Nye was describing. Yep.
Here's how to read a graduated cylinder. You have to have it at eye level.
You do.
That's the only way to read it.
And what's the bottom of that curve called that we read? Does anybody remember that?
Meniscus.
It's the meniscus, right? And so again, we'll review the good techniques for that when we get closer to our lab. So the base unit for liquid volume is going to be the liter. Right? Again, we can use the small version of this by putting the milli in front of it, the milliliter. Or we can make the big version of this with the kiloliter, KL. Notice how the L's are capitalized. It just makes it stand out a little bit better. Doesn't get confused with the number 1. And it has happened sometimes when people don't capitalize the L and somebody else is looking at their work, like it does get confusing. So we just try to get in that habit. And I talked about that last year too, right? So if we're talking a solid now, if we have something that is an irregular shape, so like my Panaboard pen, there's no formula that I have for volume of this solid pen, right? I have a formula for like the volume of a rectangle that's solid. I have a formula for a pyramid or for, a lot of other different shapes, cylinders, circles, right? We have all those formulas, but if there's a lot of things in our world that are weird shapes. So we have to have a way to find the volume, okay? So if we have an irregular shape, we'll use that water displacement. If it's a regular shaped object, there's a formula. So like for a square or a rectangle, you have length times width times your height, right? So for a pyramid, half the length times width times height. Volume of a cylinder, you have pi times your radius squared times the height. So you can look up all those formulas if it's a regular shape. So all of these regularly shaped objects have formulas, right? The units are always going to be some version of the meter. So a centimeter, a meter, maybe a kilometer if like you're dealing with something really, really big, right? But the base unit is always going to be some version of the meter. Typically for us, it's going to be the centimeter, okay? And so if we're going really small, it might be the millimeter. Big version, the kilometer. It's always going to be cubed or raised to the third power because you're taking a length unit times a length unit times a length unit, or a meter times a meter times a meter. So you get a meter cubed, or a centimeter times a centimeter times a centimeter cubed. Okay. So I told you guys this story last year. It's a little embarrassing. I feel confident sharing my embarrassing moments with you guys. When I was in high school, I didn't realize why volume was cubed. I just memorized it. I'm like, okay, when I'm dealing with volume, always cube it. When I'm dealing with area, it's always squared, right? Never occurred to me until I was in college and I was doing something and all of a sudden I was like, oh my gosh. It's because you're multiplying 3 length units together. A centimeter times a centimeter times a centimeter. That's to the 3rd power. That's 3-dimensional. I was like, oh my gosh. Why did I not know that? Like, it was really embarrassing. I was like, whew, like, it just hit me out of the blue. Then I got thinking, area. Area is length times width. That's 2-dimensional. That's why those units are squared. I just memorized it, never thought a thing about it until I actually, like, I don't know what, like I said, just hit me. I was like, whoa. Like, so I like to share that with you because sometimes when you understand why something is the way it is, it helps it make a little bit more sense. So that's my embarrassing moment. I was 20 years old and I did not realize why it was cubed and why it was squared. It's the truth. So hopefully I saved you from a little bit more years of embarrassment for yourself. You don't have to memorize why it is. It's just like understand, like, okay, yeah, I'm multiplying 3 things. I'm going to have that as a cubed unit. Or I'm only multiplying 2 things. That's why it's going to be, a squared unit if we would be talking about area. So, yeah, that's one of my many embarrassing stories that you'll hear. Okay, so if you look at the rectangular formula of length times width times height up here, you're multiplying the length 3 times. A centimeter times a centimeter times a centimeter, that's where the cube comes from. Oops, sorry. So, if we're dealing with a solid, it's going to be something cubed. Raise that unit to the 3rd power. Okay. Okay, now, if the solid is an irregular shape, and Dylan is all over this, he's ready to do it. If it's an irregular shape, then we have to use the water displacement. Displace means out of place. Dis means like if you dislocate something, like you dislocate your collarbone, you have located it away from where it should be. Okay, don't do that. I've heard it's really painful. So if I have an original volume in this graduated cylinder and I put this irregularly shaped object, so it's not a perfect square, it's not a perfect circle, it's not a perfect cylinder or pyramid, right? It's a weird shaped rock. I put it in there and it displaces the water, right? It raises the water away from its original position because that rock is now taking up the space that used to be taken up by water. 1 second. And so if I take my final volume from my original volume, the change was caused by the rock, and that's the volume that I'm trying to find, so it works just perfect. Yes?
Like the water is like air. When you put an object in it, it displaces and the water level raises, and then you do like the density and then do some subtraction and it should work.
It does work. And we, like I said, we'll do this in one of our labs. If you find the volume of the water with the original amount of volume, original volume of that water, and then we drop in the irregularly shaped object, and then we can find the new volume, or that final volume. And so if we subtract the new or the initial, that should be final. Yeah, that should be final right there. If we subtract the new and final volume from the original. So this is slide 8. I didn't catch that. So that should be final. So if we take the final volume from the original initial volume, what we're going to be left with is the volume of that rock that caused the displaced water to move. Okay, so if we take a look at this, all right, so a quick review. There are given numbers on a graduated cylinder, all right? Those given numbers are gonna be the ones I look at. And then I need to know what each space is worth because not all my lines are marked. So it's not like it says 10, 11, 12, 13, 14, right? I need to figure out what each one of those spaces is worth. So if I take two of my given numbers, right? Two right in a row. If I take 15 minus 10, what is that? That's 5 milliliters, right? So if this is 5 milliliters, right here, right? If I take that, then I know that in that area I have 1, 2, 3, 4, 5 spaces. So if I have if I have 5 of my milliliters broken up into 5 equal sections, each one of these sections is really another milliliter. So that tells me what each space is worth. And again, we'll review this more when we get closer to our lab. But if this is the 10 line, 11, 12, 13, 14, that does get me to 15. So now I know what each space is worth. So if I'm at 15, I go to 16 and 17. They actually call this 17.1. I don't really like that because 0.1 is not marked on this. Like, that is not a line. This is to the whole milliliter, not the 1/10 of a milliliter. I think they're just trying to show you that that's a little over 17. I would be happier with it being 17. And this one actually just kind of rounding up to 20. That would have been just fine for 20 and 17. But the initial volume, they're saying is 17.1. The final is 19.8. So if you subtract this from this, that will give you the volume of your rock, I guess, right? And so if we now have the volume that we calculated, they gave us the mass. From there, we would be able to find the density of this because we have the mass now and we have the volume. So from there, we could go on and do density. And so this is going to be really similar to the lab you're going to do with the metal cylinders, right? You'll have an initial volume, you'll have a final volume, you'll subtract it, you'll use that volume and the mass that you measured, and you'll calculate the density. Okay, so let's have a little bit of kind of concept about what is density? Like, what's it look like? What are you talking about when we say it's very dense or it's not very dense? Okay, so let's take a look. So which one do you think would have the greater volume? If you have a kilogram of feathers or a kilogram of rocks, what's going to take up more space to make a kilogram? What do you think?
Feathers.
Feathers? Think how many feathers you'd need to make one of these, right? That'd be a lot of feathers, right? But you could probably pretty easily find a rock that has about the same, that would be small enough that, wouldn't take up a whole lot of space, right? Which one's going to have the greater mass if you have 1 kilogram of feathers or 1 kilogram of rock?
Obviously the rock.
You think the rock?
Yeah.
Who thinks the feathers? Okay.
I'll go with
You go with what?
Will.
With Will? Anybody have a different answer? Cade?
They're the same
Why?
because it says it right there.
1 kilogram and 1 kilogram. That is the same, right? So the mass would be the same because it's saying 1 kilogram of each. But the amount of space that it would take up, you'd have a lot more space for your kilogram of feathers because you'd need a whole bunch of them, right, to make up that kilogram's mass. You might have a rock that's super small and it's just really, 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 really tightly packed. So, it wouldn't take up very much space at all, but it'd still be 1 kilogram. It'd be that same mass. You're not changing the amount of matter that's making it up. Okay, I think that this one kind of helps show a little bit visually what's going on when we're talking dense versus not dense. So it's defined as the mass per unit of volume, or how much mass is in a given amount of space. How tightly packed are those molecules, basically. All right, so if I have the same volume, look at this little gray box here, right? If I have this volume, they're the same. So if I have the same amount of volume, same amount of space that they're taking up, which one is more tightly packed? The one on the left or the one on the right? So raise your hand if you think the one on the left is more tightly packed. Okay, anybody like the one on the right? Okay, so you have a good concept of what density is. That's good. All right, so if you look, you can see there's not a whole lot of open spaces. Here, these look like water molecules where they are forming this like kind of tetrahedron where they kind of form and leave this gap in a way. So these open spaces mean that it is not as dense. Okay, and that's how density is. Think of it as how tightly packed are those molecules. Pretty tight, not as tight. All right, so let's take a look at this. So I see equal sized squares. So the volume that they're taking up is the same. So volume is the same. I have 1, 2, 3, 4, 5 molecules. This one I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, about 20. Which one is more dense? Raise your hand if you like the one on the left. One on the right. So good. Told you a lot of this would be a review. Now, let's switch it up. Let's change the volume. All right? So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So now, like, the masses are the same, but we have changed the volume. Which one is more tightly packed? Raise your hand if you like the one on the right. Raise your hand if you like the one on the left. Okay, so this one's more tightly packed because the volume is smaller. Okay, good. Let's stop there. So that is slide 13. All right, we had a video